Hello and welcome to this next section on deep learning and specifically at the moment, artificial neural networks. Although this topic is equally applicable to the convolutional neural networks that we will learn about and apply later in this section. And this is an exciting topic and one that we've been nicely building towards. Here we're going to be talking about activation functions, which as we've touched on in the prior tutorials are some logic that will essentially determine whether a neuron will fire or be activated or if it will not. Or in terms of an artificial neural network, what value it will pass on to the neurons in the next layer. We are going to be taking a look at what activation functions are, why they exist, what they do, and the different types that are commonly utilized. Before we do that, let's very quickly recap what we have covered so far. So in our neural network, our data enters the network via the input layer with a neuron for each input feature. From there, these values are passed to the first hidden layer. And for simplicity, right now, I'm just showing a single neuron in yellow existing in a single hidden layer. This passing of information also takes into account unique weighting values on each connection and a unique bias value for that receiving neuron. We use this formula here to multiply each input value and its corresponding weight value, and then we add all of those up. After which we add our bias value. And for now, let's call the result of that entire calculation Z, or Z if you prefer the American pronunciation. And you can see that represented in the middle of our yellow neuron. From there, this value is passed through this mysterious activation function, which determines the output value of the neuron. And this is the value which is passed on to either the neurons in a subsequent hidden layer or the neuron or neurons in the output layer. It doesn't really matter either way. What is important to absorb is that an activation function dictates the output of a neuron based upon the input value, which we are referring to as Z. These activation functions are very important. There are many types and you will be responsible for choosing which one to apply. So we'd better get moving and start discussing what exactly an activation function does and why. And the best place to start thinking about why is simply heading back to this here, where our formula gave us our value for Z. And as we discussed in the last tutorial, this function is a linear function, the very same as we'd seen in the tutorials on linear regression. Now, if we just used a bunch of linear functions in our neural network, then we really only give ourselves the ability to solve linear problems. And to give a really simple example here, I'm just illustrating a hypothetical classification problem where we want to classify data points we have as either blue or orange based upon some input data that we have in the form of X and Y values. A linear classifier would be able to achieve this. It would find a straight line that represented this boundary pretty well. And to be honest, this would be a great solution in that case. But what if we're not dealing with a linear problem? What if our data looked like this? Well, our linear model is going to struggle. It can only fit a straight line, something like this, or perhaps it would try this. And well, neither of those solutions are really very good. We actually need a non-linear solution. We need something more like this, where the boundary actually has a sort of a curve to it, or in other words, the solution needs to be flexible at different points in space. Again, this is still super hypothetical at this point, but hopefully it shows why enforcing some non-linearity to our solution can help solve quite complex problems. When each neuron is transferring information through the network using a linear function, even with many layers of many neurons, we're still somewhat bound to a linear solution. However, when each neuron has its own non-linear output, the solutions can end up being pretty flexible. Cool, so that is a high-level look into why we might apply activation functions in a neural network. I mentioned earlier that there are some different types of activation functions, so let's run through some of the popular ones now and take a look at how they transform our input data into the non-linear output that will be passed on. The first activation function is something you might have learned about already, especially if you have run through logistic regression here in Data Science Infinity, so you are going to hit the ground running. The activation function that I'm talking about is the sigmoid activation function. In our logistic regression example, we were taking in log odds values for each of our data points, and these ranged anywhere from negative infinity to positive infinity. We then used the logistic function to essentially squish these values down, ensuring that they existed somewhere between 0 and 1, a range for which we could think of them as probabilities of our output being true. In the case of a neural network, this squishing ability is exactly what we want from our sigmoid activation function. It will take in the values of z, which we calculated here, and then essentially force that value to instead exist between 0 and 1. And you can see the formula for that over on the right. The sigmoid value, which I'm just referring to here as f of z, or z with the function applied to it, is equal to 1 over 1 plus e to the power of minus z. And we covered this in more depth in the logistic regression tutorial, so feel free to head back there for a refresher if you need. But the important thing to really know here is that with a sigmoid activation function, if our value for z, which we see along the bottom of our chart on the x-axis, had a value of 0, then this would end up with an output value based on this transformation of 0.5. If our value for z is a number greater than 0, then our transformed output will be some number approaching but limited by 1. So no matter how big z is, the output value will never exceed 1. And of course, the same would apply for negative input numbers, where our transformed output will be some number approaching but limited by 0. So the output values from each neuron in our network, in other words, the value that is passed onto the neurons in the next layer, will always be values between 0 and 1 if we apply a sigmoid activation function. And I guess you could say that neurons with an output value nearer to 1 are more activated in this case, and those with output values near to 0 are less activated. But either way, some positive value is being passed on each time. So that is the sigmoid activation function. Now, there is actually an even simpler activation function, and this was what was used in the very early neural networks, and this is simply called a step function, or what is sometimes known as a threshold function. And this only provides two possible output values, 1 or 0, nothing in between. If our z input value is greater than or equal to 0, then our output is 1. Otherwise, our output is 0. This has been found to be somewhat limiting in terms of the neural network's learning ability, but mathematically and computationally it is very efficient, and it really resembles more accurately this idea that we have around the neurons in our own brain, which is quite binary. They're either activated or they're not. Now, more similar to the sigmoid function is another commonly used activation function called the hyperbolic tangent function, often just written as tanh. And you can see that this has a curve somewhat similar to sigmoid, although if you look closely on the left-hand side, you see that this activation function squishes our values between -1 and +1, rather than 0 and 1 like we saw with sigmoid. All right, next I want to show you what is probably the most commonly used activation function in use today, and this one is called ReLU, or more formally the rectified linear unit. Here, any value for our input z that is below 0, so any negative input values, will be output as 0. Otherwise, it will be output simply as the input value itself. And you can see that in action with the formula over to the right of screen. Our output is simply equal to whatever is largest out of 0 or our input. As an example of this, if our input value z was -2, then our output would simply be 0. If, on the other hand, our input z value was equal to +2, then our output value in this case would also be +2. And this would apply for any positive z value. So an input of 4 would give an output of 4, an input of 50 would give an output of 50, and so on. This particular activation function essentially blocks neurons with negative input values by assigning them an output of 0, but it allows neurons with positive input values to continue flowing unfiltered. A question you might have about ReLU is, why is it so popular? Well, there are two reasons, one very simple and one quite complex. The simple one is that it is very lightweight from a computational point of view. It doesn't really have to transform anything. It is simply taking the maximum of two values. And this means training our network, which remember is the process of passing information forward through the neurons and then back again to update the weights and bias values over and over again, is much more efficient. In some cases, we have thousands or millions of parameters that need updating many times. So if we can have a fast activation function, this makes a massive difference for the overall training time. The second, slightly more complex reason ReLU has become popular is because it helps to eliminate something called the vanishing gradient problem. And this is something we often see with activation functions such as sigmoid, where we get these very small output values. And this on its own is fine, but as backpropagation takes place and we need to calculate the gradients to understand what movements we should make with the weights and the biases, these small values compound on each other as we move back through each hidden layer, meaning the gradient values get smaller and smaller and essentially vanish, meaning that information is somewhat lost and the neurons end up just existing with values of 0, so no real learning can take place. So like I said, ReLU, or the rectified linear unit, is very common to see, and we will be using it in the practical tutorials later, so keep an eye out for it then. In saying this, even ReLU can suffer from issues in more complex scenarios. This idea that any negative inputs are just slammed with a 0 output means you can end up with a lot of essentially dead neurons. And to get around this, you might sometimes see another related activation function called leaky ReLU, which is very similar but just allows some small negative slope for input values that are negative. You don't need to worry about this too much for now, but it is good to understand what it is, as I am sure you will see it referred to as you progress further into deep learning. Now, before we wrap up, there is one more thing I want to discuss. And to do this, let's head back to this image here, which looks at the structure of our entire neural network. In most cases, you'll end up using the same activation function for all the neurons in all of your hidden layers. You don't have to, but in most cases, this works pretty well. So let's just go down a common route and say in this particular network, we want to apply the ReLU activation function. So we would apply this to these neurons here, meaning ReLU would dictate the output values that are passed onwards to be the input values for the neurons in the next layer. For the next hidden layer, we would again apply ReLU, and again this would dictate the values that are passed on to the next layer. Now in our example here, this next layer is the output layer, and this is where things get interesting in terms of activation functions. We still want to apply an activation function to the neuron or neurons in our output layer, but we need to think about what these activation functions do in order to apply the correct one here. In our example network on screen, as we are dealing with a regression problem, we have one neuron in our output layer, and we want this to hold the value for our prediction. So if this value was the number of lemons Lucy would need for her lemonade stand, or the sales for a grocery store, or the price of a house, we wouldn't want that value to be squished in a way that forces it to exist between 0 and 1, for example. So we wouldn't want to use the sigmoid function here. In the same way, we might not want our predicted values to be capped at 0. Depending on the problem, we may need negative predictions, so we wouldn't want to use ReLU here either. In the case of a regression problem, we would most likely just want to apply a simple linear activation function, where the value that comes into the output neuron is the value that we use as our prediction. There isn't any capping or transforming here, just what comes in is what comes out. And just for completeness, this activation function when plotted would look like this here. Where things get much more interesting is if we were looking to solve a classification problem, and also whether that problem is a binary classification problem, in other words, only two outcomes, so cat or dog, yes or no, or if we're solving a multi-class classification problem. For example, predicting if an image is a cat, or a dog, or a mouse, or a horse, or a cow. In the case of a binary classification problem, we may actually still only have one neuron in our output layer, and this would just end up holding the probability that any data point is of the positive class, which might be cat in the cat versus dog classification problem. The reason we'd only need one output neuron is that if there's an 80% chance of the image being a cat, as there's only one other option, we can equally say that there is a 20% chance of it being a dog. Having a neuron for each is somewhat redundant in a binary case like this one. And as a very quick extra side note, we wouldn't actually use an artificial neural network to solve an image recognition problem like this one. We would instead use a convolutional neural network. But to illustrate the different scenarios, it works well. Everything we're covering in this tutorial is 100% applicable to convolutional neural networks as well, so it's extremely valuable information to store away in your brain as we keep building up our knowledge of how all of these amazing deep learning solutions work under the hood. Anyway, for this particular scenario where we are dealing with a binary classification problem, we would want the value of that output neuron to be a probability. And since probabilities exist between 0 and 1, we would want to plug in our Z value for the output neuron. And remember, this Z value is calculated by summing up the inputs multiplied by the corresponding weight values and then adding the bias value. And here we can see over in the green neuron to the right of screen, that just happens to be 1.4. As we really want this value to exist as a probability, we would just plug 1.4 into the sigmoid activation function. And as you can see on screen, this would give an output probability of 0.8. So in this case, we would say there is an 80% probability that the image was of a cat. Of course, how accurate that probability value actually is somewhat dependent on how well our neural network has learned from the training data over time. But the important thing is that it makes sure this represents a value that makes sense for the task at hand. Now, the third type of problem we discussed was the multi-class classification problem. And when dealing with these, we would typically have a neuron for each of the classes, as we need each to be represented. In this example, let's again say we are looking to classify image data, and this time we want to know if an image is of a cat, a dog, or a cow. In this case, we often use another type of activation function on our output layer called softmax. And all you really need to know here is that the softmax function will take the values of all the output neurons and force them all to add up to 1, which can be very, very useful. Let's take a really quick look with an example. Let's say that the Z values that each of our output neurons were holding, in other words, the values that each of those neurons had calculated by summing up their inputs multiplied by the weights plus the bias value, were 3.1 for cat, 0.9 for dog, and negative 1.2 for cow. These are somewhat useful on their own. I guess we could probably say that the image is most likely a cat as it has the highest value, and that it is very unlikely to be a cow as that has a very low value. But what would be much nicer and much easier when trying to explain the outputs as well as compare them to others that we may have would be to turn these values into something more akin to a probability. The formula for the softmax function, which will do precisely that, is this here on the right. Now that looks quite complicated, but as always, if we break it down, it all starts to make sense. Firstly, that lowercase e that we see in the formula is Euler's number, and we've seen that before as it forms part of what we need for our sigmoid function as well. It is just a mathematical constant equal to approximately 2.718. So let's do this. That top line of the equation just tells us that for each of our output neurons, we will calculate e to the power of its z value. So for cat, which has a z value of 3.1, we would get e to the power of 3.1, which I can tell you is about 22.2. This process would be exactly the same for our other output neurons, and if we ran those calculations, we would get 2.46 for dog and 0.30 for cow. And it's worth stopping for a second and noting that even if our initial z value is negative, as we see is the case for cow with negative 1.2, this is completely fine. They just get turned into a very low positive number. And now that we've got these new values, that bottom line of the equation is simply telling us to add them up. And doing so gives us 24.96. Now we've completed the top and bottom lines of the equation, let's do what the whole thing is telling us to do, which is to divide each of our new values by the total that we just calculated. And if we do that for our first value for cat, we would get 22.2 divided by 24.96, which gives us 0.89, or what we could say was a probability that the image was of a cat of 89%. If we did the same thing for the other two neurons, for dog and for cow, we would get values of 2.46 divided by 24.96 for dog, which gives approximately 0.10 or 10% probability, and then 0.30 divided by 24.96 for cow, which gives about 0.01 or a 1% probability. So once we've applied the softmax function to our output neurons, we end up with very clean probabilities across all classes that add up to a total of 1, or a total of 100%. In our example here, like we discussed, we could say that we're pretty confident that our image is of a cat, we're pretty sure it's not a dog, and we're very sure it's not a cow. Again, of course, like I mentioned when we were talking about the binary classification example, how good those predicted probabilities actually are is somewhat dependent on how well our neural network has learned. And these final values for our outputs, whether it be from our multi-class classification example here, our binary classification example where we use sigmoid to get probabilities between 0 and 1, or our regression example where we just applied a linear activation function, they would be compared to the actual outputs when calculating our loss, which you remember is essentially the mismatch between the predicted and actual outputs. And this is what drives the network to head back through in the backpropagation process and update all the weights and biases in certain directions in order to lower that overall loss value. And how exactly the network calculates loss, how it does this backpropagation, and how it uses gradient descent to alter the weights in the correct direction is what we will cover in the next few tutorials. For now, however, you should be so proud that you know all about these very important activation functions, where they exist in the network, how they help the network solve complex non-linear problems, as well as the different types that are commonly used depending on what we need them to do for us. And I've just put this down here on screen as a bit of a recap or a guide that you can use whenever you are constructing a neural network. To run through this, so for regression problems, you're most likely going to be using the ReLU activation functions for your hidden layers and then a linear activation function on your output layer. For binary classification problems, again, ReLU is commonly used for the hidden layers, and then you would most likely use a sigmoid function on the output layer in order to get that single probability value between 0 and 1. And then for your multi-class classification problems, again, ReLU for the hidden layers, and then a softmax function on the neurons in the output layer to ensure that you get some nice, clean probabilities that add up to a total of 1 across all of your classes. Now, very quickly, I want to give you one more tidbit of information regarding this. At some point, you may find yourself looking to work on what is known as a multi-label classification problem. This would be where instead of trying to categorize this image here as either cat or dog or cow like we did in our example earlier, we might have an image like this which contains both a cat and a dog. In other words, multiple labels on a single image, and hence the name multi-label classification. And we can actually do this, but we just want our output neurons to have final values that tell us the probability that each animal exists in the image. And in this case, we wouldn't want all of those output values to add up to 1. So we wouldn't use softmax. We would instead actually use sigmoid, where it would give each output neuron its own independent probability between 0 and 1. So I just thought I'd mention that in case you ever do want to solve a problem like that. Anyway, this has been a lot of fun, and it is extremely valuable knowledge to have, and it will all start to make even more sense once we get to building our very own neural networks in Python. For now, let's keep moving onwards in this very exciting deep learning adventure, and I will see you in the next tutorial.